Dear all, a very good morning. In the previous lecture, we had discussed about ATE, that is automatic test equipment that was required for testing of any device. It is a very expensive tool and it is required for generating multiple patterns, typically in order of millions or billions, which can be utilized for testing the device. Thereafter, we looked at some of the different types of tests, like test after manufacturing, such as BIST, built-in self-test, OLT, online testing, and so on. We had looked at their examples. Then we had a brief idea about functional testing and structural testing. What are the advantages of functional testing over structural testing and vice versa? Mainly we looked at the advantage of structural testing over functional testing. Okay, now in the present video lecture we are going to look at the fault models. Okay, what are different type of fault models and what are their equivalents for different circuits that will be utilized. Okay, so let us begin. Okay, so fault model, error is a representation of a defect. That is, if there is an error in any circuit, it means there will be a defect in that circuit. Okay, let us take this this multiple input AND gate which has got 5 inputs and we have got an output here. If we apply inputs 1, that is each of these input is given a logical value 1, then answer in the normal case should be, logic output should be 1. However, if there is an error, like if a line is broken here and so on, then the output will be 0, because we know that the truth table of AND gate, if any single input is 0, then the complete output of the AND gate becomes 0. Okay, so this breakage in line can be modeled as an error or 0. Okay, so we will see how these faults are modeled or errors are modeled in the form of faults. Okay, a line is called a net. So each individual lines, whether at the input or an output, is known as net. Okay, so what is fault? A fault will be stuck at 1, normally represented SA1, or stuck at 0, normally represented by SA0. At fault level, we check whether net is having a defect or not at both inputs and outputs. So whenever we are checking the faults, we will check if any net is having stuck at 1 fault or stuck at 0 fault, either at input or at the output terminal. Okay. Now, types of fault models. There are basically two types of fault models: single line stuck at fault model and multiple line stuck at fault model. Normally, single line stuck at fault model is most utilized. Okay, let us look in brief about these fault models. Multiple line stuck at fault model. Okay, this is a representation of multiple line stuck at fault model where we are having 3 input AND gate and a 2 input OR gate, and this line is stuck at 0, this line is stuck at 1. Okay, so in this case number of possible faults is 3 to the power n minus 1, where n is number of nets. Now, single line stuck at fault model, here we take only one net at a time. So if we have got this circuit, suppose where we have got 3 AND gates, each having 2 inputs, then fault can be at each of these points which has been represented by X. However, we will take only one of these error at a single time. Another thing is that we have to look at which of the error will propagate forward to the other errors or not. Like if there is an error here, so this error will propagate to both the AND gates. However, if an error is here or here, of any of one of these spaces, so this will not affect this net and this will not affect this net. However, this error will affect this net. So this is the fault which will propagate to the both the fan outs. However, any fault at a single fan out will not affect the another fan out. Okay. Now, thus we take only one net fault at a time. If n nets are there, then there are possibly 2 to the power n faults, either stuck at 0 or stuck at 1. Single stuck fault model is manageable in number and also provides acceptable quality of test solution. Okay, so utilizing single stuck fault model is very easy as compared to checking multiple stuck fault levels. Okay, therefore these are easily manageable in number and they also provide a very good test quality. Faulty nets are permanently set either to 0 or 1. So in whichever net we want to test whether there is a fault or not, we will set it to permanently either 0 or 1, and then we will see the effect on the output of our circuit with respect to different test patterns. Now, the branches of fan out nets are independent with respect to the location and effect of stuck fault. Okay, so fan outs are not much affected depending upon where the fault is at. Okay, so let us take a very simple example. If this is an AND gate and we have given inputs input 1 and input 2, both are equal to logic 1. Okay, and suppose this net input 1 net is stuck at 0. So in normal case I will get 1 because both the inputs are 1, but if there is a fault then I will get an output as 0. So whenever I get an output as 0, it means that a fault has been encountered, and if I get an output as 1, it means that it is a normal and there is no fault. So I1 was stuck at 0 fault. In a similar way, multiple AND gates can be checked for such type of faults. Now, what is the advantage of such a technology or such a methodology? There is no need of extra pins, multiplexers or shift registers, etc. So we have reduced the requirements of extra pins, multiplexers, shift registers, and therefore our hardware requirement is low. Now, what is the disadvantage? Disadvantage is that we have not tested the functionality, that is complete functional testing has not been done, which takes a lot of time. And this disadvantage actually has an advantage that even if we have not tested the functionality, we are getting 99.9% accuracy with structural testing at fault levels. Okay, next we are going to look in brief about the fault equivalence of a single stuck fault model. Okay, this means what stuck fault at the input is equal to particular stuck fault at the output. So two stuck faults F1 and F2 are equivalent if the output function represented by the circuit with F1 is same as the output function represented by the circuit with F2. This means let us assume that there are two faults in the circuit, F1 and F2. Now I will check the output of the circuit with respect to F1 and see what is the output. Then I will check the output of the circuit with respect to F2 and look at the output. If the output after F1 and F2 faults are same, then both the faults are called equivalent faults. Okay. In structural testing with stuck fault models, one test pattern can check more than one fault. Therefore, by applying a single test pattern, we can check more than one faults. Okay, like in this circuit, if we are applying a pattern 0, 1, 1, 1 and so on, we can check more than one fault in a given circuit. So let us briefly look at different equivalent faults for basic gates. Okay, for an AND gate, okay, stuck at zeros at the input is equal to stuck at 1 at the output. Now what does this mean? This means that if in this AND gate I am having inputs 1 1, so output should ideally be 1. However, if this is at stuck at 0, I will get an output 0. Okay, now if this is not a fault, here is a fault and it is stuck at 0, I will get an output 0. So because of this fault or this fault, I am getting output 0. So both of these faults are equivalent. Now again, looking at output, if this is stuck at 0, then and both the inputs were 1 and there were no errors here, then again I will get output as 0. So this fault is also equivalent to any of these two faults. Therefore stuck at 0 at the input is equal to stuck at 0 at the output. In a similar manner, let us look at OR gate. If we have an input pattern 0 0, output should be ideally 0. However, if any of these one line is stuck at 1, I will get an output 1. So if this is stuck at 1 and rest are fine, then I will get an output 1. If this is stuck at 1 and rest are fine, I will get an output 1. Similarly, if this is stuck at 1 and rest are fine, I will get an output 1. So these three faults are having the same output for a particular test pattern. Therefore, I will say that stuck at 1 fault for OR gates are equivalent. Okay, then looking at NAND gate, 0 zeros at input is equivalent to stuck at 1 faults at output. Okay, why is this? Okay, let us see. If I am applying a pattern at the NAND gate, okay, and I have to get an particular output. Okay, what is the normal truth table for AND gate? If I am getting a single one, I'll get an output as 1. However, if I get both the ones, I will get an output as 0. Okay, so if I will apply an input 1 and 1 and there is no fault, then I will get an output as 0 for the NAND gate. However, if at the input any of the one line is stuck at 0, okay, so I will get an output as 1. Okay, so therefore both these stuck at faults are equivalent. At the output side, if the line is stuck at 1, so no matter if I have applied 1 1 here, output will always be 1, which should have been 0. So stuck at 0 fault at the input is equal to stuck at 1 fault at the output. Then come NOR gate, in which stuck at 1 faults at input is equivalent to stuck at 1 fault at 0. For NOT gate, if input is stuck at 0, then output is stuck at 1, and if output is stuck at 1, then input is stuck at 0. If I look at fan outs, the output just propagates. Whatever fault is here, the same fault will be at the fan out nodes. Okay, I think this is sufficient for the present lecture. In the next lecture, we will look at some of the questions related to fault equivalence and see how they are dealt with. Thank you.